Okay, so quick refresher on gas laws. So, and literally, in my brain, I give gas law lectures in two different versions. There's the chemistry version of gas law lectures, and then there's the physics version of gas law lectures. It's the same kind of relationship, but the units are completely different. So, when you look at pressure, the fundamental idea of pressure is that it's force per unit of area, okay? So, and it's simple, like, okay, you take your hand, I can push a little bit on it, okay, or I can push a lot. So it's how much force there is per unit of area. So because of the fact that in a physics class we work off the MKS system, that unit is going to be newtons per square meter, okay? So in science, if there's ever a unit that has an identity crisis, it's pressure, because pressure can be measured in so many different ways. So if you've ever checked the air pressure in your tires, okay, what units is that measured in? PSI, pounds per square inch, okay? So in your standard atmospheric pressure, which is about what we're under right now, the basic idea is that one way to define it.
Awkward.
Okay. Times.
It's kind of cute flowers.
What are we doing next Wednesday?
What?
Hopefully we have no assignment next Wednesday.
Wait, why?
It's my birthday.
I hope we do have.
Isn't that when we start our finals? No. We start our finals on Friday. Our physics one and
Wait,
our
when's our meiosis test?
Thursday. Tomorrow.
Oh, really?
Well, no, we're just comparing them. We're comparing ones versus Thermo.
So
Yeah.
it's a test?
So they're gonna be like 20 points again.
I really hope it's that chart where it's like 2, 4.
Yeah, right. She has to throw in some word answers.
Whatever. It's fine.
Never happened
I
before.
gotta get hydrated. This has
Okay.
0 sugar.
Oh my God.
OMG.
Are we still there? We're still there.
Yes.
Okay. All right. So one way to define pressure is.
The hall.
My friend. Okay. He's here. So one atmosphere is your typical atmospheric pressure. So if you look at the fact that we're here having this discussion, is the fact that our rock has an atmosphere. If we didn't have an atmosphere, we wouldn't be here. And not only is it cool that we have an atmosphere, it's a very specific makeup that allows it to exist. So we're about 77% nitrogen and about 22% oxygen. So nitrogen is basically inert, okay? Doesn't react. Oxygen, very reactive. So if the roles had been reversed, if we had been like 77% oxygen and 22% nitrogen, we probably wouldn't be here having this discussion. Mainly because of the fact that if you look at how hard it is to put out a fire at 22% oxygen, and oxygen is typically the limiting factor in a fire, imagine if we were 77% oxygen. If you ever started a fire anywhere, basically you would not be able to put it out because of the fact that you would have such an abundance of oxygen. So it's cool that we have an atmosphere, and it's cool that we're 77% nitrogen and 22% oxygen. And that even that has changed. So when the Earth first formed, we basically didn't have any oxygen until a certain, I can't remember the name of it, there's a bacteria that started to produce oxygen gas. Oh, okay, cool. Then we had oxygen. So it isn't like the Earth formed and we said, oh, here's oxygen. We had to make that oxygen. And even if you look at like a relative scale, so imagine like this is an apple, and that's the size of the Earth. If you cut that in half, that red layer of skin around the apple, that's our atmosphere on a relative scale. So what keeps us from the horrible things of space, ultraviolet radiation, X-rays, gamma rays, small little meteorites, things like that, is that red layer on that apple. That's what allows us to exist. Without that, we're not here. So it's kind of cool that we do have an atmosphere. So if you look at what's creating this pressure, what we're going to define as one atmosphere, that's the basic idea. So if you look on your equation sheet, let me give you an equation sheet. Okay? So, why that's there, I don't know. So, right here,
Is that a frog?
I don't know. So, you have one atmosphere, and here are some conversions that you're going to need to know right up here. So this is going to be these last three conversions in the top left corner of your equation sheet. There's a conversion from pressure, there's the ideal gas law constant, and there's a conversion from Kelvin to Celsius. So, one atmospheric pressure is equal to 14.7 psi, which is also equal to 101,300 pascals, which is 101,300 newtons per square meter, means the same thing, which is 101.3 kilopascals, which is 760 millimeters of mercury, which is also 760
Oh, this is
torr.
not on here.
No, I know.
Which one do we have to know?
The only one you're going to have is this one.
Okay.
Okay? I'm just pointing this out, that this is why pressure has an identity crisis.
Is it
Oh, okay.
Pascals? Oh yeah, Pascal, that's
Now.
the little chameleon from Tangled.
Huh?
I was like, where have I heard Pascal from? It's the chameleon.
Well,
Have you seen that movie?
yeah.
What? I love Tangled.
Pascal's
What?
triangle.
Okay, anyway.
Oh, Pascal.
Simmer. Okay. Now, so if you look at what is fundamentally creating pressure, though, and there's two words that I hate. Do not ever say the word, oh, there's air molecules. Shut it. It's horrible.
So what's
Okay?
it called then?
There's no such thing as an air molecule. Okay? You have nitrogen, you have oxygen. Little water, little carbon dioxide. There's no such thing as an air molecule.
Cho
Okay?
chom chom.
Stop it. So, but if you look at what's creating pressure, is the fact that you have billions upon billions upon billions of these tiny little particles we can't see. We can feel them, like if we move our hand through it, oh, now we can feel them, right? But these are bombarding your skin, and they're bouncing off. And whenever they hit and they bounce off, that generates this tiny amount of force. So the collective amount of that is what's creating pressure. Now, to give you some perspective, so here you have Hank, okay? And Hank weighs roughly about 15 pounds, okay? Roughly.
Sorry.
So if you look at that 14.7 pounds per square inch, so what this means is that you have the weight of a Hank pushing down on every square inch of you right now, okay?
Really?
Yes. Every square inch of you has the weight of a Hank pushing down. Now, the one thing I want you to get out of your minds is the idea that, oh, pressure only acts downward, okay? Pressure acts in all directions, because if pressure only acted downward, you would put your hand down, and then imagine you have a weight of a bowling ball only pushing down on the top of your hand, okay? You'd never be able to lift it up, okay? You'd have this huge pressure differential. So, the pressure acts in 3 dimensions, okay? It just doesn't act. We talk a lot about, oh, the atmosphere is pushing down on you, and it is, but it's also pushing in all directions. Otherwise, you'd be like in a vacuum or a pressure shadow on the bottom side of your skin, and your blood would boil on the bottom, and you'd be pushed down on the top. So it's cool that it acts in 3 dimensions. Now, the other way to view this, and this is the one that we're going to use most often, is this 101,300 newtons per square meter. So if you get a little bit creative, here's a 1 kilogram mass, technically weighs 9.8 newtons, okay? Let's round it up to 10, okay? So this thing weighs 10 newtons. So what this means is if you have a square meter, okay, so visualize this, you have a square meter, right? And if you had if this weighs 10 newtons, okay, so if you drop off at 0 and you have 10,130. So what that means is if you have a square meter, that's like having 10,130 of these in that square meter pushing down, okay? Because that's an equivalent amount. So imagine this. You have 1 square meter. You'd have to have over 10,000 of these in that area creating that pressure. And you go, oh, that's a lot. Okay? And it is. But that's what we're used to. Now, that changes, obviously, if you've ever driven up into the mountains, okay? Or if you've flown in an airplane, okay? Your ears sense that change in pressure. Or if you dive to the bottom of a swimming pool, okay? You can sense that change in pressure. So the pressure isn't a constant, but it does change depending upon your altitude. So basically, as you go higher up, there's less pressure because it's almost like a cheerleading pyramid. If you're at the bottom of that pyramid, you're carrying the weight of everybody that's above you. But if you go higher, if you're higher up on the pyramid, you have less of that weight above you, so that's why the pressure is less as you go higher and higher and higher. Okay, so pressure created by these tiny, tiny, tiny bits of matter, hitting, bouncing off, hitting, bouncing off. We're going to work in pascals, named after Blaise Pascal, the French physicist who came up with the concept, which is also 101,300 newtons per square meter. So that's going to be your pressure. That's what we're going to work on. Now, if I'm giving this lecture in a chemistry class, pressure is going to be measured typically in atmospheres or millimeters of mercury, but typically we work in atmospheres. So that's why I said I always have to keep track of which lecture I'm giving. Now, in physics, because we're in the MKS system, the volume is going to be in cubic meters. Now, here's where the magic happens. On the pressure side, that's newtons per square meter. On the volume side, that's cubic meters. So, I lose one of those, I get newton meters, otherwise known as joules. So the left side of the equation, the PV side, gives us joules, which is a measure of energy or a measure of work. Okay, hold on to that thought for the lecture for tomorrow. Okay, so the left side of this equation is going to be joules. So if we're going to balance it out, what does the right side of the equation have to be?
Newton meters?
Or joules, right?
I mean, yes.
Yes. So the N, anybody remember what the N is?
Particle number.
Number of moles, right?
Oh.
You were a little
Number of moles.
Number of moles, right? Okay, so that's going to be in moles. So we're going to have to flash back to Chem 1, okay? No! Mole conversions. Get over it. It's not that bad.
Oh, I was just kidding. I just forgot. Anyway.
Okay?
That was me that said that. That was
Okay.
yeah. Why do you always think it's me?
Because that, I don't know, I just do.
Stuck up for he always thinks it's me. It's her.
Okay.
It's me.
R.
Now, R is this value on the front. That's your ideal gas law constant. And it's 8.314. And we'll talk about the units here in just a second. That's joules per mole Kelvin. Okay? Kelvin is going to be the temperature scale that we're going to use.
What the heck is that?
And then this temperature has to be in Kelvin. So this is where the magic happens. So you have N, which is moles. You have temperature, which is Kelvin, which we'll talk more about in just a second. And then you have R, which is joules per mole Kelvin. So then the moles cancel out, the kelvins cancel out, we get joules. Okay? So that way both sides of the equation have the same units. Okay. Now let's talk about temperature. Temperature is kind of a weird thing. So here I've got your old school thermometer, and the thermometer is reading about 22 Celsius. So we have three primary scales that we work with. We have Fahrenheit, which is what, especially us in America, that's what we typically use. So the analogy has been made that human beings are very good at detecting small measures of change. So we can actually pick up the subtle differences between like 70 degrees Fahrenheit and 72 degrees Fahrenheit. So Fahrenheit is what humans feel, okay? Celsius is what water feels, okay? Because what happens at 0 degrees Celsius? Water freezes. What happens at 100 degrees Celsius? Water boils, okay? So that was a nice benchmark, okay? They said, okay, hey, this is a universal thing. Water is basically going to boil at the same temperature. So at the time they were establishing the scale, they chose water. It's like, oh, okay, everybody can make water freeze. Okay, at that point, we're going to make a mark on this thing and go, we're going to call that 0 when that water freezes. And then we're going to take that thermometer and then we're going to put it in water, and when that water boils, we're going to make another mark that says that's 100. And then we're going to divide that in between with 99 marks, and we're going to say each one of those is 1 degree Celsius. So Fahrenheit is what humans feel. Celsius is what water feels. Kelvin is what atoms feel. Okay? So, named after Lord Kelvin. So, the beauty of the Kelvin scale is that you have what's called 0 Kelvin, which is known as absolute 0. So, the Kelvin scale is a measure of what's called the entropy of the atom. Entropy is the measure of the disorder. So, my room tends to have a pretty high state of entropy, pretty high state of disorder. And as particles get colder and colder and colder and colder and colder, there's less and less and less disorder because the particles aren't moving around as much. So a great analogy is if you look at, and we're going to spend a lot of time explaining thermodynamics in terms of second grade class named Timmy, okay? So anytime I'm talking about Timmy, picture a hyperactive little second grader, okay? Who, if you give him Skittles, gets very, very excited, okay? Just stay with that analogy, okay? So imagine that you have a room full of Timmys, and they're out at recess, and it's like 70 degrees. Nice day, okay? They're going to be going, wah! Okay, they're going to be running around, right? There's going to be a certain amount of disorder because they're second graders and it's 70 degrees outside and they're on recess, right? Now imagine that you take that same group of second graders and you put them outside, and it's like minus 20 Fahrenheit. So what's going to happen to the amount of disorder with those second graders?
It's going to decrease.
It's going to be less because they're going to be huddled around like, oh, it's so cold, okay? So there's going to be less entropy because there's going to be less random movement. So at 0 degrees Kelvin, this is what's known as absolute 0. So at that temperature, the entropy of an atom, which is the measure of the disorder, goes to 0. This is a theoretical value, okay? 0. Theoretically, we can get to that point, and we've come close to it, like 0.00001 Kelvin. And the only way we did that was trap an atom in some lasers so it couldn't move. So the advantage of the Kelvin scale in terms of this equation is that it has two advantages. Number one, it's never going to go to 0. Because if the temperature goes to 0 over here, that means the left side has to go to 0, which means either the pressure goes to 0 or the volume goes to 0, which doesn't make any sense at all. Okay? Worse yet, we never have negative numbers in Kelvin. Because if you have a negative temperature over here, that means either the pressure is negative or the volume is negative, which makes even less sense. Okay, granted, maybe we can have 0 volume, which doesn't make much sense, but okay, maybe. Certainly can't have negative volume. So every temperature has to be in Kelvin. You cannot work in Fahrenheit, you cannot work in Celsius. Whenever you are working with gas laws, pressure can be in different things, volume can be in different things, R has different values depending upon the units. But the temperature always, without fail, has to be in Kelvin. Now the next logical question is, Mr. Burkamp, how do we get Kelvin? Well, that's that little conversion up there. So right now, according to the thermometer, we're at about 23 degrees Celsius. Okay? If we look at this, we're at about 23. So if you want to go from Celsius to Kelvin, all you have to do is add 273. You don't have to do anything weird. You don't have to multiply by 5/9, 9/5, whatever. Just add it together. So right now, we're at about 296 Kelvin. Okay? That's the temperature that we're at right now. So a funny thing happens, though, if you look at how thermometers work. So thermometers basically work like a second grade class of Timmy's. So imagine down here, this is the old style thermometers, but they work well in this case. So here's like the classroom of second graders. And this here is like the overflow kids that the teacher can't handle. So these are kids that have been sent out in the hall. Okay? It's like, here's the classroom, a certain number of kids are out here in the hallway. So what I'm going to do is I'm going to grab this and hold this in my fingers. So we were at 23. So as soon as I do this, you'll notice that this column begins to rise. Okay? So basically what's happening, and this is where the Skittles come in. So energy is flowing from my hand into the classroom. So this is like the room mother showing up and going, class, we have Skittles. And Timmy goes, I love Skittles. Okay? And Timmy starts flipping out. And the teacher says, Timmy, I can't handle you right now. You need to go out in the hall and take your little vagrant friends with you. So when I'm doing this, I am giving Skittles to the kids. Teacher can't handle it. It says, more of you out in the hall right now. Go. Okay? Same number of kids, but I'm going to put more of you out in the hall. As a matter of fact, right now, we're all the way up to like 32 degrees Celsius. So this temperature has raised 10 degrees. So what's happening is that I'm giving thermal energy, I'm giving Skittles to the Timmies that are inside the classroom. Teacher says, can't handle it, you, out. So we have taken a bunch of kids that were in the classroom and sent them out in the hallway. Same number of kids, we've just changed the location of them because we gave them Skittles. Now, what would happen if I take this and I put it in a glass of ice water? What would the temperature do? It would decrease. Why? What are you doing with the Skittles?
Taking them away.
You're taking away, okay? Kids are going, oh, man, you took away my Skittles. Oh, sadness. And so then the temperature would drop because the teacher's going, okay, you're more calm, all this is back in the classroom. So that would begin to drop. So temperature is fundamentally a measure of Skittles with the second graders. Higher temperature, they have more collisions, they're more excited. We get Skittles! Okay, and they flip out. Okay, so that's what temperature is. Now, an interesting thing happens on the way to the change in temperature. So we went from 23 degrees Celsius to 33 degrees Celsius, right? Temperature change. It changed 10 degrees Celsius, true? Now, if we're in Kelvin, that's 296 Kelvin, and we're changing that to 306 Kelvin, okay? If I add 273 to 33, I get 306. So notice that's a 10 degree change in Kelvin. So this is going to be important when we begin to look at change in temperature, which we're going to spend a lot of time talking about. So even though the temperatures themselves aren't the same, but a 23 degree change, or excuse me, a 10 degree change in Celsius is the same thing as a 10 degree change in Kelvin, okay? So changes are the same, okay? Changes are the same. The temperatures themselves aren't the same, but the temperatures are the same. Okay, now, let's look at what happens when we begin to change some things. So over here, I've got you're going to have to spin that camera around a little bit. So I've got a balloon inside the chamber.
Does it have to stay plugged in?
Huh?
Does it need to be plugged in?
No.
Okay.
So inside here, I've got a balloon. So what's creating the pressure inside the balloon?
The bouncing of the atoms.
Yeah.
The
Nitrogen,
molecules.
oxygen molecules are hitting the sides and they're bouncing off them. Cool, right? Okay. Now, there's also pressure on the outside of the balloon because there's an atmosphere, right? They're bouncing around on the outside. So what I'm going to do is I'm going to turn this on and I'm going to remove the gas that's inside this chamber. I'm going to create a vacuum. So when I do that, what do you think is going to happen to the size of that balloon? You can do one of three things. It could just stay the same because I'm going to have the same number of particles in there. I'm not going to change the temperature. Everything's going to stay the same. The balloon won't change. Situation number two, the balloon is actually going to get smaller because of the fact that I've removed the balloons on the pressure on the outside, so the elasticity of the balloon is actually then going to allow that to collapse and get smaller. Or the balloon's going to get bigger because now you don't have the pressure on the outside, but you have the pressure on the inside. It's going to try and equalize it, and the balloon's going to get bigger. So it's going to stay the same, get bigger, get smaller. So how many think the size of the balloon is just going to stay the same? How about get smaller? 1, 2, 2 on the small train.
Remember, this was in
Get bigger.
kindergarten.
Vast majority thinks it's going to get bigger.
Nope.
No. This isn't Chicago. You don't get to change your vote, man. Okay? Mags, why do you think the balloon's going to get bigger?
Because there must be like pressure on the outside of it, like keeping it in, and all of the molecules on the inside are still trying to move, so it can get more space.
Okay, I like that. I like it. So I'll turn it on.
Wow.
Wait, is it getting bigger?
Yeah, it is.
Whoa, it's getting bigger.
Is it gonna pop?
Whoa, it's getting bigger.
It's gonna fill up the whole thing.
Did you say air molecules?
Yeah.
Did you really?
Doc points from
Okay. So here's a little historical lesson in how this, what this demonstration says. So if you look at World War II, Second World War II, they had, the United States had certain long-range bombers, primarily B-17s and B-22s. It's not important. But they weren't pressurized airplanes. They were open. Windows were open. So as the planes were flying at higher altitudes, like 30,000 feet, number one, it was really, really cold. Number two, it was very, very low pressure. Okay? So what they figured out very early on with the bombing crews is that they would not allow them to eat beans. Because what happens when you eat beans? What do you get? You get gas. So imagine this is your intestine at 30,000 feet. Okay? And you have gas inside of it. So what's it going to do?
Expand.
It's going to expand, right? So here you are at 30,000 feet, very, very cold. You're being shot at by enemy planes, and you're doubled over in pain because of this demonstration right here. So they said, okay, y'all can't eat beans, because they didn't want the gas in the intestine that would expand at very, very high altitudes. But then when they would come back down. Now, if you ever go scuba diving, you remember this. The opposite work is when you go scuba diving. If you go scuba diving, you go below the surface, the pressure actually increases because you have more water above you pushing down. So what happens, you get what's called the bends if you depressurize too quickly. If you come up too quickly, and if you're way, way down, what happens, literally, your nitrogen in your body, or the dissolved oxygen, will actually boil. It will go from a dissolved state into a gaseous state, and that's horrible as well. Now, if I pull this out, okay? So at that point, Mother Nature, the story is, Mother Nature abhors a vacuum because it's an imbalance. So what happens was that Mother Nature tried to equalize everything. So all these little nitrogen and oxygen molecules that were hitting the outside said, oh, look, now we can go in. So Mother Nature is going to try and equalize that pressure. Okay, so the old joke is, Mother Nature never sucks, science never sucks, you just have negative pressure. And as you equalize that pressure, that's what happens. Okay, so spin that around. Now, typically with gas laws, what you do is you look at comparisons. And so what I'm going to do is I'm going to show you how to solve about 95% of all gas law problems very easily. So you have PV equals nRT. 95% of the time, you're not going to change the number of moles in the gas, and you're certainly not going to change the ideal gas law constant. So what we're going to do is we're going to keep that the same, and we're going to divide by T. So you get P1 V1 over T1 equals P2 V2 over...
See, it was her, not me.
And that's why I'm staring at her.
Everyone, you don't know that? It's like the equation.
It's called the combined gas
That
cell.
was like all of chemistry, literally for me.
And I'm going to show you how to do them all in 5
And
minutes.
this one was
Okay.
a perv nerd.
And this comes out of purple.
That's
Okay.
all of him wanted.
So here's the deal. So let's look at what we just did. Okay? This is where this works. So you intuitively understand it.
Oops.
As the pressure decreased, what happened to the volume?
And expanded.
As I
It
decreased
got bigger.
the pressure, the volume got
Increased.
bigger. Okay? So what you do is that you cover up the variables that stayed the same. In this case, I didn't change the temperature. So I'm going to cover up my temperatures because those, I don't care what the temperatures are because I'm not going to change them. This works only if you're making a comparison of changes. So we're covered that up. So since the temperatures remain constant, this is why this works. You have pressure 1, volume 1. Okay, I don't care what it is, it's pressure 1, volume 1. Pressure is going to be typically be in atmospheres or pascals. The volume is going to be in cubic meters. Okay? Now, look at what happened. As soon as I hooked it up to that vacuum, what happened to the pressure inside that chamber? It decreased. So pressure 2 became smaller. Right? Pressure 2 became smaller. But we have to equalize both sides mathematically. I have to have the exact same number. So if I shrank the pressure, what had to happen to the volume?
It got big.
Volume 2 got bigger. Okay? Makes sense. Okay? You intuitively understand this. There's an inverse relationship between pressure and volume. Okay? Now, let's talk about temperature. Okay? Let's say I take this syringe, which sounds odd, okay, and I throw it into an ice bath. What do you think is going to happen to the pressure inside that gas if I throw it into an ice bath? Increase or decrease? If I throw this into an ice bath, what do you think is going to happen to the pressure inside that syringe?
Increase.
How many votes is going to increase? I'm going to throw it into an ice bath. I'm going to take away Skittles.
We're going to decrease it.
Oh, yeah.
That was my second answer.
Temperature's going to go down. I'm going to take Skittles away from the little kids.
And I was like, that
The
doesn't
kids are
make
going to
sense.
be. So visualize this. This is a horrible thought. Visualize this. I'm actually teaching second graders. Horrible thought. Little ankle biters, right? They're literally just colliding with my legs. No, that's true. I've done like demonstrations for like second graders, and literally, high school. Okay, so, huh? The what? Yeah, yeah.
Wait, what?
And so,
Because I'm in ice cream? Wait,
No,
no.
he would come and demonstrate. I
So,
I don't know, so yes. Sorry.
So pressure, my pressure, is reflective of the number of kids that run into my ankles, right? Right? Right. True. So if we're outside and it's really, really cold, right? I'm not going to have as many collisions because the kids are just going to be huddled around. Versus, oh, mom shows up and she gives them all Skittles. Oh, this is working, we got Skittles. Ah, okay. I start running into my legs and I'm going to flip out because my pressure is going to go up. Okay? So temperature is a reflection of Skittles, which is a reflection of energy. Okay? So if you look at this, let's say that we're going to keep the volume the same. We're not going to change the volume of the syringe, right? So if you look at this in terms of P1 V1 over T1 equals P2 V2 over T2. So we're going to keep the volume the same. So I'm not going to worry about my two volumes because that's going to stay the same. I'm just going to have the same size syringe. Volume's going to stay the same. So then if I cross multiply, I get P1 T2 equals P2 T1, right? So initially, I had a certain amount of pressure and I had a certain amount of temperature, right? Now, I'm gonna put this thing into an ice bath. So what's going to happen to my temperature? Temperature is going to become smaller. So to balance it, what has to happen to my pressure?
It has to become tiny.
it has to go down as well, because the particles are going to have less energy. Now, so if your car is equipped with sensors that measure your air pressure, and you get little warning lights that go off if your air pressure gets too low, is that typically going to happen in the winter or in the summer? In the winter. The Timmies have less energy, okay? They have less energy. There's going to be less air pressure in your tires. Pressure's going to drop. The warning light's going to go off. Now, it's 120 degrees outside, okay? You're driving through the desert or on a black asphalt road, really hot. What's going to happen to the temperature of your tires? It's going to go up. What's going to happen to the pressure? It's going to increase. Okay? Makes sense. Got it? Good. Okay. So, bring that camera, we got it in the back. When you heat up a metal, do you think it expands or contracts? Why?
More Skittles.
More Skittles. Okay? Kids are going to be vibrating more. Ah! Okay? They're going to occupy more space. So, I've got this piece of metal like you, right? So this is actually two different types of metal that are very thin, but they're glued together. So I'm going to heat this up, and as it heats up, it curls. Okay? So the reason it's curling is that metals expand differently depending upon the type of metal that it is. So each metal has what's called a different coefficient of linear expansion. So the reason that that's curling this way is that the metal that's on the inside isn't expanding as much as the metal that's on the outside. So imagine that you put your hands like this, and you begin to curl it over. So that metal that's here on the inside is expanding at a smaller rate than the metal that's on the outside. So that's why it's pushed over like this. So if you've ever seen the thermostat in your house, some houses still have, you haven't gone digital, there's like a little slider on your thermostat. And that's how you set the temperature in the house. So what happens, how that mechanism works, is that it's made out of a situation like this, where you have two different metals that are glued together. So as the temperature in your house changes, the pitch of that metal inside that thermostat changes. And so what you do is you set your thermostat at a certain point. So if it gets, like in the wintertime, if it gets too cold, then it slides up, it hits that point, it completes a circuit, it tells the furnace to kick on. And then that furnace runs until the house warms up, and that curls back down, you lose contact with that point, the furnace shuts back off again. The opposite happens in the summertime. If it gets too warm, it gets too warm, curls down, makes contact with that point. Or house cools down, it expands, it goes back up. Okay, so now I've got this set up. So this is brass, and this is designed where this fits exactly just within this gap, okay? So what I'm going to do is I'm going to warm this one up. So as that warms up, what do you think is going to happen to the volume of that piece of brass? Increases, right? We're giving Skittles to the kids, right? So we're giving them lots and lots and lots of Skittles. Okay? It's like Skittles on steroids. Well, that might be a bit much, okay? That might be a bit much.
I feel like today's an important day.
So as I get that really, 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 really warm.
It's Pearl Harbor.
It's Pearl Harbor?
What?
Oh my gosh, is this so
It's Pearl Harbor, actually?
Yes.
Okay? So now when I go to fit that in there, now it won't fit. Okay? So this won't fit because of the fact that that metal expanded so much that that won't go. Now if I cool it back down,
Close up.
then I've taken away the Skittles, and now it fits back in there. So now let's talk about the one that has holes. So this will fit in there, but it's a pretty snug fit, okay? It'll go, but just barely. So I'm gonna take this, and I'm gonna heat this one up. So I'm gonna heat this one up as a whole one. So one of two things is gonna happen. Either the hole is gonna get smaller, the hole is gonna get bigger. So how many think it's going to get smaller? I'm gonna heat this up. Hole's gonna get smaller. Why?
Volume is bigger.
Bed is going to expand, and it's gonna close that up. How many think the hole's gonna get bigger?
Wait, what?
One. Why, Cooper?
Because it's expanding.
Because it's expanding. Okay. Now, keep in mind, okay, this goes in, but that's a tight fit. Okay, it'll barely go in there.
Yeah.
And Cooper, why do you think it's going to get bigger? Cooper, it's expanding. Seems reasonable. Okay? So I take this, kind of roll it around and around and around.
Bunsen
Get it really,
burner.
really hot. And it actually goes in easier.
OMG.
OMG. Now, it expands. And here's the reason why. Imagine that was still a solid piece of metal. Okay? Imagine it was still a solid piece of metal. And I heated it right in the middle. That would expand outward. Okay? It would expand outward. So imagine that we heat it up, then we cut it. Okay? And then we let it cool down, and then everything would contract back. So this is why that hole actually gets big. It's somewhat counterintuitive. You think, well, it expands, it should close that up. But it's actually expanding outward from that center, and that's why that happens. Got it? Good? Great? Back we go.
God, press.
I earned this.
Wesleyan.
Okay. And yes, you will have this sheet on the test. You don't have to have it memorized. So what this is, down here at the bottom, there's a whole bunch of stuff we're going to need for the next unit. Specific heats, densities, values of thermal coefficients of linear expansion. So what this is that it lists the material, and then it lists this numeric value. So what you have is this, you have this equation, L equals L naught times 1 plus alpha delta T. And it's kind of a jacked up unit, because one thing about this is that this is your L naught, which is oddly enough your initial length. This alpha has units of Celsius to the -1, and this is going to be your change in temperature. Now, listen to me. It's subtle, but it's important. Notice that it's not the temperature. It is the change in the temperature, okay? So what that means is as your change in temperature gets bigger, this new length is going to get bigger. As the length of the material itself gets bigger, the new length is going to get bigger. So there's a direct relationship between the initial length of the material and the change in temperature. Now, oddly enough, if there is no change in temperature, guess what? There's no change in length. And the final length is going to be the same as the initial length. Okay? Now, this is why this only has units of Celsius to the -1. Because that change in temperature is going to be Celsius. It is not the temperature. It's the change in the temperature. So what happens is that your Celsius cancels out, so everything in here has no units, because the units cancel out. Then you're taking a numeric value that has no units, you're multiplying that by L naught, which might be in meters, centimeters, whatever it is, and then you're going to get the final length. So this is why this works. Doesn't make any difference. Man,
Was it the pen?
it was. It still is. Okay, it still works. So here's the deal. This is why it has the units that it does. So the bigger the change in temperature, the bigger the length, the bigger the final length is going to be. Now, you also have area ones down here, where you have area equals area naught times 1 plus 2 to alpha delta T. So in area, why do you think there's a 2 in that equation? You're talking area. How many dimensions are in an area? Two dimensions. You have length and width. So therefore, that's why there's a 2 in there. And again, it doesn't make any difference what that area knot is going to be in. So like on your assignment today, I'm going to give you a square that's 20 centimeters by 20 centimeters. You can just leave it in centimeters. It doesn't have to be in meters because it doesn't make any difference. Okay? Could be in centimeters squared, could be, it doesn't make any difference because it's all the same ratio. Now with volume, you have volume equals V naught plus 1 plus 3 alpha delta T. Why is there a 3? Volume has 3 different dimensions. Okay? So stop that camera.
Is there a 4th dimension?
Okay, so when you get to question like, for example, number 7. So order the volume of cubic centimeters occupied by 0.2 moles of oxygen under pressure of 2 atmospheres and a temperature of 20 degrees Celsius. What are you going to have to do with the atmospheres? Change them into what? Pascals or newtons per square meter. What are you going to have to do with the temperature? Change them into Kelvin. Okay? When you get to number 9, you have 2 atmospheres, temperature of 20 degrees. Then I'm going to change it. What's going to be the new pressure if the temperature is raised to 40 degrees Celsius? Okay? Temperature is going to go up. What do you think is going to happen to the pressure? It's going to increase. So you know your answer has to be bigger than 2 atmospheres. But again, I cannot emphasize this enough. Do not leave that temperature in Celsius. It won't work. It only works if it's in Kelvin. When you get to questions number 13 and 14, you're talking about area and volume. You can just leave those in centimeters, okay? It's 20 centimeters by 20 centimeters. If you're really hardcore and you want to change them to 0.2 meters and 0.2 meters, fine, okay? But I'm just telling you, it doesn't make any difference. Math is probably a little bit easier if you talk about leave them in 20s, but if you're really hardcore, you can change them. Okay, I'm done. You're on your own. Be free.